Good evening, class. This is Mr. Eggleston, and this is lesson 6.3, absolute value functions for Algebra 1. What we're going to do is the learning targets are we're going to interpret and graph scenarios that can be modeled with absolute value functions. We're also going to connect the meaning of absolute value functions as describing distances between points to the shape and symmetry of the graphs. All right, just as a quick reminder, what does an absolute value do? Absolute value of 3 is equal to 3. Absolute value of negative 3 is equal to 3. What the absolute value does is it spits out the distance. The number on the inside is away from 0. So if this is 0, and we have 3, 1, 2, 3, and negative 3, 1, 2, 3, and that's negative 3, and that's 3, this distance right here is 3 units. Likewise, this distance right there is 3 units. So the absolute value gives you the distance away from the 0 point, from the origin. Okay, and that's basically what the absolute value does. So when you see that the absolute value of negative 20, you know that's just positive 20. If you see the absolute value of 20, you know that's also 20. That's the idea. Okay, moving on. Here's the activity. How many gumballs are in the jar? Mr. Wilcox has a jar of gumballs. His students will guess how many gumballs are in the jar. The student who guesses closest to the correct amount wins the jar of gumballs. Below are some of the guesses that students made. All right, so you got Abigail. I'm kind of partial to that name. That's my daughter's name. Has guessed 45. Bryant guessed 30. Carmen guessed 25, and Dominique guessed 37. Based on this information, how many gumballs do you think are in the jar? Well, one way of figuring this out, or guessing, would be to find the average. So I'm going to do that. I'm going to take 45 plus 30 plus 29 plus 37, add them up, and divide by 1, 2, 3, 4. As saying that's as good a guess as any from this information. So 45 plus 30 plus 29 plus 37, that is 141 divided by 4. That works out to be about 35.25, and since we can't have a 0.25 gumballs, I'm going to say there are 35 gumballs in the pot or in the jar. Okay, that's just finding the algebraic average, the arithmetic average is what they refer to it. Now, here's some information. The graph at right shows the number of gumballs guessed, X. So this is number of gumballs guessed. And the Y is the number of gumballs away from the correct amount. So Y is the number of gumballs away from correct number. Okay. So, for example, A, Abigail's guess was 10 gumballs. Now remember, Abigail was at 45. So Abigail was over here, and they're telling you that she is 10 gumballs away. So what we can do is plot over here 45, 5, 10. It'll be right there. That's Abigail's. I'll call that A. Okay? On this plot. Bryant's guess was 5 gumballs away from the correct amount. Add point B to the graph. So at 30, he was at 5. Okay. And that's point B. I'm putting it off to the side because we're going to be doing something with these dots. Carmen tied with Abigail. Okay. She was also 10 gumballs away. So Carmen, who guessed 25, was right here. Notice, whereas Abigail looks like was 10 gumballs away higher, Carmen was 10 gumballs away, but she guessed less. Okay. Dominic won. He was 2 gumballs away. So where was Dominic at 37? 5, 6, 7. Oh, didn't mean that. All right. So 5, 6, 7. He was 2. All right. So there we go. Now, what does that do for us? You could try to graph something that, goes like this, and maybe does that, but that's not what we're after. It stands to reason that if these are true guesses and they're relatively accurate because, well, they tell you how off they are, we could draw a line like that and then connect these dots with a straight line. And you see where they cross is right there at 35. So it looks like 35 gumballs. That's where the two lines meet. Now, it's also what the average was too, right? Didn't we say if we found the arithmetic average, it was about 35 gumballs? And it turns out it is 35. Okay? Give 2 more guesses that would count as a tie. What they mean by that, if you guessed, I don't know, right there, there's another one. That's a tie. That's right there. In other words, it's the same distance on either side of this point here. Okay. And describe the graph. It forms a V. Write a rule that gives y numbers of gumballs away from the correct amount for any guess x. This is the equation. Y equals the absolute value of x minus 35, like that. Okay? Notice, if you're 10 less than 35, if you're at 25, and you guess 25 and it comes out that you're 10 less, that would give you 25 minus 35 absolute value. That's going to be 10. Or if you guess 10 more, in which case it was 45 minus 35 absolute value, that's also 10. So you see, it gives you the distance away from the true value your guess was. All right? So basically, that's that right there is 5 units less. And this one is 5 units greater. Okay? So there you go. Now here's the quick notes. Absolute value function. The absolute value parent function is y equals absolute value of x. Okay? The domain is all real numbers. As you go up to the right, You're going to cover all the positive x values. And if you go up to the left, you'll cover all the negative x values. So the domain, which is all x values, is all real numbers. The y values, notice this graph stops at y equals 0. Matter of fact, it's at the origin. So, and it doesn't go below the x-axis. So the range is y is greater than or equal to 0. Okay. Sorry about that. Okay, shifted absolute value functions. All right, there you go. Basically, A is the steepness. H is the shift h right, x minus h, and plus k shift k up. The graph is symmetric over the vertex. So let me give you an example of absolute value graphs using Desmos. We're going to graph y equals the absolute value of x, okay, minus, now I'm going to throw in the letter h. All right, add slider. Now we're going to change the value of h as we go. And then we're going to add plus k. Okay, so we have these. Notice as, oh, sorry, I was supposed to add a slider. So there we go. Now, I'm going to show you what happens when we change the value of k. All right, as k gets bigger, notice the absolute value graph does not change its shape. It just moves up and down the x-axis. Okay, if k is positive, it moves up, like at 7, k plus 7, so that'll be up 7 units. All right, and then when it's negative, it drops it below the x-axis. Okay. Sorry. Now, let's try and see what h does. As h gets bigger in the positive direction, notice it moves to the right. So that's absolute value of x minus 4, moves it 4 units to the right. X minus 5 would be 5 units to the right. X minus 10 would be over here at 10 units to the right. And if it's x plus a number like x plus 5, absolute value of x plus 5, notice it moves it left 5. So when the number's holding hands with the x, it moves it along the x-axis. And when the number's outside, it moves it up and down. And what's kind of cool, we can do this and this. And all of a sudden, we're changing both, and you see it just kind of moves around the grid. All right? So, all right, where the two graphs meet, this point right there, the word for it is vertex. Okay? That's the vertex. And the vertex is where the two lines meet. And you're going to find out that you're going to want to always know where the vertex is. And the slope of the lines is going to be whatever a is, the number in front of the absolute value. So if a is like 2, the slope is 2 over 1. You would go up 1, 2 to the right. So theoretically 1. Up 1, 2 to the right, 1. All right. That's if this number was 2. If it's 1/2, you go up 1 to the over 2. And you'll see this as we do this. So now, and that's it for the activity. Next comes the check your understanding.